So let us try to illustrate, right, again this abstract transfer function over the sign abstract domain, right. So over the sign abstract domain, right, we have already defined various things, right. So we have defined what are the elements, right, in sign abstract domain. So this is just plus minus and bot. We have also given an ordering, right, which is the less than or equal to relation, right. So this was this relation, this plus minus and then plus minus, and using this, right, this is a complete lattice, so therefore it also defines the join. Okay. So the only thing, right, so now as a designer, right, of an abstract domain, along with giving the ordering and the join relation, you also need to provide the abstract transfer functions, right. So this particular sign abstract domain, right, it clearly satisfies the first two requirements, right, which is that D is a complete lattice and alpha and gamma, they form a Galois connection, right. So for alpha and gamma, right, we have again, right, we have come up with a generic procedure, right, for computing alpha and gamma. So if you recall, right, we had said that this alpha, right, this essentially maps a set of program states to the smallest set in the abstract domain, right. And similarly gamma of D was just defined to be D itself, right. So this generic alpha and gamma that we had computed, they are guaranteed to form a Galois connection, right. So this sign abstract domain is satisfying the first two properties, complete lattice and Galois connection. So the last property, which is that every abstract transfer function must be a consistent abstraction of the concrete transfer function, right. So let's try to design such an abstract transfer function for the sign abstract domain. So now since we can have an arbitrary number of program variables, right, we will define this sign abstract domain D to be this map from V to these four values, right. So earlier we had said that D itself was this, right, but now in earlier examples we only had either one variable or two variable, right. But in general, if you have an arbitrary number of variables, for every variable you need to assign a sign, right. So which is one of these four signs, right, and this is my sign abstract domain now, right. So again you can show that if, right, that this itself is also a complete lattice. Okay. So earlier we had shown that only this set itself is a complete lattice, but you can show that this D is also a complete lattice. Okay. So let us try to compute the abstract transfer function for an assignment statement, right. So let's consider some assignment statement x colon equal to E, right, where E here, right, is some arbitrary expression, right. So let's assume that it's a linear expression, right. It's so it's a term, right, essentially in the theory of integers, let's say. Okay. So now when we want to compute the abstract transfer function, right, f hat p of this particular statement, right, we need to make sure that it's a consistent abstraction of the concrete transfer function, right. Now what does this statement do, right. So this statement changes the value of the variable x but leaves the value of the rest of the variables unchanged, right, which means that if I take f hat p of D, right, where D, let's say, is some element of the abstract domain, so D is going to assign a sign to every variable. The sign of all other variables except x should remain unchanged, right. For x we need to compute its new sign. Okay. So this f hat p of D, right, this is going to be the same as D, except that the value of x will change now, right. So the value of x may potentially change, right, which means that the sign of x may potentially change, but the sign of the rest of the variables will remain as it is, right. So we use this particular notation, right, we have defined this earlier, right. So this notation means that this is a function, right, this whole thing is a function which is the same as the function D, right, except for the value x, right. And for the value x, the new value, right, of for x, right, will be given by this g of D comma E, right. So this g D comma E is another function that we are going to compute. Okay. And what, I mean, you can guess what this is going to do, right. So this is essentially going to compute the sign of this expression E. Okay. So we are assigning this expression E, right, the value of this expression E to the variable x. So we need to find out what could be the sign of this expression E, right. Will it always be positive, will it always be negative, or will it be some arbitrary value? Okay. So g of D comma E, this is what we want to compute, and this we will express inductively, right. So remember that this E itself is an expression, right. So E, right, will have E will be something like, let's say, E1 plus E2 or E1 minus E2, right, where E1 and E2 themselves are expressions, so on, until it reaches some program variable, right, let's say, which is in this case is the program variable y. Okay. So this is the base case, right? So this is where this expression E itself is just the variable y. Okay. So if you are doing something like x is equal to y, where y is a program variable, then the sign of y is going to become the sign of x, right? So g of d comma y is simply going to be equal to d applied over y, right? Remember that d itself is a map, right? So d is a map from v to the signs, right? Plus minus and bot. Okay. So if you are doing x equal to y, then the sign of y becomes the sign of x. Okay. Now if your expression is something like e1 plus e2, right? So if you are doing something like x is equal to e1 plus e2, then you need to recursively compute the sign of e1 and e2, right? So suppose the sign of e1 is plus and the sign of e2 is also plus. So now you are adding two positive values, so therefore the sign of e1 plus e2 is also guaranteed to be plus, and that will become the new sign of x. So the new sign of x will become plus as well, okay, because the sign of e1 plus e2 is also plus. Okay. Similarly, if the sign of e1 is negative and the sign of e2 is also negative, then this e1 plus e2 is guaranteed to be negative. But for every other case, it can be arbitrary, right? So if e1 is, for example, positive, e1 is positive and e1 is negative, or rather e2 is negative, or the other way around, right? If e1 is negative and e2 is positive, right, then it could be, then the sign of e1 plus e2 can be anything, right? So therefore we will assign the value plus minus. Similarly for e1 minus e2, right? So now here, if the sign of e1 is positive and the sign of e2 is negative, right? So remember, you are doing e1 minus e2, if the sign of e2 is negative, it will become positive now, right? So therefore the value of e1 minus e2, right, the sign of e1 minus e2 is guaranteed to be positive, and that will be the new value, or rather new sign of the variable x, right? Similarly, if e1 is negative and e2 is positive, right, then again e1 minus e2 is guaranteed to be negative. In every other case, we cannot say, right, what will be the sign of e1 minus e2, therefore it will be plus minus. Okay. So this is a consistent abstraction, right? This is a consistent abstraction of the contrary transfer function for x colon equal to e, right? So again, you can try to sort of reason about why this is a consistent abstraction, right? Because we are always making sure that we over approximate the actual effect, right, of executing this particular program statement, right, over the concrete domain. Okay. So f at pi of bot is defined to be bot itself. Okay. So we have completed one part of the picture, right, which is we have shown that the abstract GOP, it always over approximates the concrete GOP, right? But earlier, right, we said that okay, we have this abstract forward propagate procedure, right? So we are going to apply this abstract forward propagate procedure on any arbitrary program using any abstract domain, and using this particular procedure, right, we will compute this mu hat, right? So this mu hat is what is computed according to this procedure. Now this raises some obvious questions, right? First of all, does this algorithm actually compute the abstract GOP? Right? So the definition of abstract GOP is very different from what this algorithm is actually doing, right? So the definition of abstract GOP is that you take every possible path to a location L, right, and along that path you compute its abstract transfer function by composing together the abstract transfer function of all the individual program statements, and then once you compute all of those values, right, you then take their join. Okay, but this is not what this procedure is doing, right? So it's not actually taking every possible path to every location, right? The second question is that, is this algorithm itself guaranteed to terminate, right? So if this algorithm doesn't terminate, right, then no matter, even though the abstract interpretation may be sound, but will not be useful, right, because we may not be able to find the abstract values which are reachable at every location, right? So this algorithm, right, this is also called Kildall's algorithm, right, proposed by Gary Kildall, and what we will actually show, right, is that this algorithm, right, it doesn't compute the abstract GOP, and it's also not guaranteed to terminate, right? So there are some conditions which are required, and only if those conditions are satisfied, then this algorithm is guaranteed to terminate. So first of all, to differentiate between this abstract GOP mu hat and what this algorithm is actually computing, we will use a slightly different notation for what this algorithm is computing, right? So we will use this mu hat k instead of mu hat, right? So recall that mu, so mu is the concrete GOP, right? So this is the concrete set of program states reachable at every location. Mu hat is the abstract JOP, and this is the join of the abstract values which are reachable at every location, and mu hat k is what is computed by Kildall's algorithm, right. So the algorithm is the same, except that I am using this mu hat k notation. Okay. So first let me demonstrate through a very simple example, right, that this Kildall's algorithm, it actually does not compute the abstract GOP. Okay. So let us consider this particular program, right, which consists of 3 locations, very similar to a program that we have seen earlier. Let us let us first try to run Kildall's algorithm on this program using the sign abstract domain, right. So here I have 3 variables, right, I, j and k. So to each variable I will give a sign, right. So assume, right, that this is I, this is j and this is k, right. So at the start location L0, I, j and k can take any value, therefore the sign assigned is plus minus, right. And so this is exactly what Kildall's algorithm does, right. So it at the initially, right, so it initializes the value at the location L0 to this alpha of p, right, which in this case, let us say, because we are saying that the 3 variables can take any value, therefore alpha of p will be plus minus, okay. And for every other location the value is going to be bot, right. So this is what I am also assigning here. So for L1 and L2 I am assigning bot, okay. Now what the algorithm does, right, is that so it is a while loop, right, where in every iteration it will take a location, right, and then propagate its value to its successors, okay. So in this case, in the first iteration it will take the location L0 and then propagate the value, the abstract value at that location to its successor, and while propagating it will also take the join with the value that was already there at that location, right. So in this case I will first propagate, right. So propagate meaning I will compute f hat. So let us say this is my program P, right. So I will compute f hat P of this plus minus and plus minus, okay. So what is going to be f hat P of plus minus, right. So now here I am assigning positive values to I and k, the value of j is not modified. So this is simply going to be plus minus and plus, right, because I and k are guaranteed to take positive values, j will continue to take any value, right. So now once it computes this new value, it then takes the join with whatever was there at that location, right. So this will be joined with bot and bot. So after doing this join, right, since bot is the minimum value, right, therefore the least upper bound is going to be this value itself, right. So you'll get plus minus and plus, and then this keeps on happening, right, in every iteration, right. So now you will propagate from L1 to L2, which means that again you will compute this f hat p, right. So suppose this is p, f hat p of plus minus and plus, okay. So here if I and k both have positive values, since you are multiplying two positive values and assigning it to j is guaranteed to have a positive value, right. So therefore this is simply going to be plus and plus, right. And I and k will remain unchanged, right. So therefore their abstract value will also remain unchanged. So we'll get plus and that will be then joined with the existing value, right. So we'll get plus at the location L2, and then you will again propagate this plus to the location L1, right. So we'll compute, so let's say this is p, so we'll compute f hat p of plus and plus, okay. So now in this particular, in these two statements, right, I am assigning a negative value to I and k, j is not modified, so I will get minus, plus and minus, and now this particular abstract value, this will be joined with the abstract value that is already there, right. So we will take join with plus minus and plus, right. So remember that for this join we will do a pointwise join, right, and this is using the sign abstract domain, right. So remember that the sign abstract domain, right, this is the sign abstract domain, right. So if you take the join of plus and minus, you will get plus minus. If you take the join of plus and plus minus, you will again get plus minus, and if you take the join of minus and plus, you will again get plus minus, right. So therefore the new value at the location L1 is going to be plus minus and plus minus, okay. And now you will again propagate this through this statement, right. So if you assume this is p, so compute f hat p of plus minus and plus minus, okay. And now here, right, since I and k can take any value, so you are multiplying I and k, but since I and k can be either positive or negative, j also can be either positive or negative, right, because I could be positive and k could be negative, right, or I could be positive and k can be positive, and so on, right. So now and of course I and k itself, right, they are also plus minus, right, so they can also take any value. So this will be plus minus and plus minus, and now this will be joined with plus plus plus, right. So again from the lattice, right, you will get plus minus plus minus plus minus, and now everything will stabilize, right. So what applying Kildall's algorithm shows, right, is that I, j and k can take any value at any of these locations. Okay, so now let us quickly compute the abstract GOP, right. So now, so for computing the abstract GOP, you consider any location, right, and you consider all paths to that location from the start location L0, right. So for example, for the location L1, right, you consider this path, right, which is from L0 to L1, and you apply the abstract transfer function of that path on this value. So if you apply that, you will get plus minus and plus, right, because I and k can take positive value, right, and j can be anything, right. Similarly, you do this for every location, right. So for example, at the location L2, I take this path L0 L1 L2, right. So L0 L1 L2, this is one path to the location L2, and then I compute its abstract transfer function, right. So if you take pi to be this, so what is f hat pi? So f hat pi, if you assume this is p1 and this is p2, f hat pi is going to be f hat of p2 composed with f hat of p1, and then you apply this composite abstract transfer function on this value, right. So again, right, if you think about what will happen, right, so since I and k have been assigned a positive value and you are multiplying two positive numbers, therefore you will get plus plus plus, and similarly you do it for all paths, right. So now at the location L1, right, I have this path L0 L1 L2 and L1. So at the end of this path, right, I compute what is the abstract value, right. So now if you do plus 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 and you apply the abstract transfer function of this particular program statement, right, as we have seen, right, you will get minus plus and minus, and then this is a new value, right, that is reachable. So therefore you collect it, right, so you will get minus plus and minus, right? So this minus plus and minus is the value that is reachable at the location L1 through the path L0 L1 L2 and L1, right. So if you execute along this path, I know that I and k take negative values while j is guaranteed to be positive, right. Similarly at L2, right, so you will get L0 L1 L2 L1 and L2. So this is another path at location L2, and if you compute the abstract value along this path, and now along this path, since along this prefix, right, the value that you compute is this minus plus minus, where I and k are both guaranteed to be negative, and if you multiply two negative numbers, then you will get a positive number, right. So therefore the value of j at this point after you execute this path is guaranteed to be positive, so else you will get minus plus minus, and so on, right. So if you do this calculation, right, across all possible paths to the locations L1 and L2, and you can do this, right, you will see that these are the only abstract values that are reachable at their corresponding locations, right. So at the location L1, these are the only two abstract values. At the location L2, these are the only two abstract values. So once you collect all these abstract values, you then take their join. So if you take their join, right, so you get that, so you see that I can take any value, j can take any value, k can take any value, and j can also take any value, right. So you will get plus minus and plus minus. So this will be the join at the location L1. So at the location L2, something interesting has happened, right, because I can again take any value, but j, right, is guaranteed to take a positive value, and k again can take any value, right. So you get plus minus plus and plus minus. So if you contrast, right, what was computed using Kildall's algorithm and what is the abstract GOP, you can see that there is a difference, right. So at location L0 and L1 they are the same, but at the location L2, the abstract GOP says that the value of the variable j is guaranteed to be positive at the location L2, but Kildall's algorithm says something else, right. It says that the value of j can be anything, right. So this demonstrates as mu hat k, right, is not guaranteed to be equal to mu hat, right. Now This is problematic, right, because our soundness of abstract interpretation was based on the abstract GOP, right. So everything was, so the soundness was based on the abstract GOP, but now we have no way of computing the abstract GOP, right, because the abstract forward propagate is computing something else, right. So Kildall's algorithm is computing something else, right. So what is it that the Kildall's algorithm is actually computing, right, and why is it still sound to use Kildall's algorithm, right. So that's what we will show, right. So we will prove that this mu hat k is guaranteed to be greater than or equal to mu hat, right. What this means is that mu hat k will always over approximate whatever mu hat is computing, right. In fact, you can see this through this example as well, right. So in the example, mu hat says that j can take any positive value, while mu hat k is saying that j can take any value, right. So this is over approximating the set of actual the actual abstract GOP for the variable j at the location L2, right. So we will show that this is in fact always true, right. So no matter what program you take and what is your abstract domain, for any program and for any abstract domain, the Kildall's algorithm values, right, they are always an over approximation of the abstract GOP. Okay. So let's end here. We will continue in the next lecture. Thank you.